So good afternoon, everyone. I wish I could see you, but I know you're there. So welcome to the Textiles Time Science Roundtable. We're going to have a short explanation of the program. Isaac and I will talk a little bit about it, followed by 4 short talks. I guess I'm all about short today. Then we'll have a Q&A at the end of the presentation, so please add your question to the Q&A. So at every session, we have decided that we're going to add a quote, and some of them are by famous people, some of them are not, and this one is by famous people, us. So yeah. Today, we're talking about our response is serendipitous wandering and wondering. You have to gain a fluency in the compatibility of unrelated disciplines. So here we go. Here's our shortest explanation we have been managed to develop. And for me, what jumps out here is really collaboration. And it's a collective of expertise that we want to harness. Isaac, anything you want?
Well, yeah, I want to point out that especially with the folks that we have here today are definitely involved in cross-field collaborations with artists and scientists to not only enhance their own research and works, but also just to invent new things, new thought, new conversation. And so this platform that we are launching here with under TSA is one of our first approaches here. And we hope to have more people continue to participate in dialogue and help us develop this as we move forward. We'll have other programming and gatherings planned in the future as well.
Okay.
Yeah, and I just want to say I'm Isaac, and I am currently in the Textile Conservation Lab here at the Art Institute of Chicago. I don't know if you all got to read a little bit about us here, but I'm here doing a full days of work, so it's been nice to be able to also join the conference and the talks while I'm doing that. Lots of exciting things happening here, and I encourage you to go to the Art Institute website. As I don't want to share any further news about what we have going on because it's not my news to share, but please do that. Yeah, Maggie, where are you?
So I am in my office with a map of the world and my dog. So if he barks, I apologize ahead of time. And we have Lindsay and Elizabeth, and we had Heather. So let me go to the order of the day. So we're going to start with Lindsay, who's going to talk about her art and how she combines science of the ocean acoustics and really talk about her time on the vessel. I am going to take you on a journey with knots. It's a naughty journey. And Heather's going to ask, can the meter be wrong? And Isaac and Elizabeth, keeping with the season of this year, they're going to be searching for ghosts. I think it's the perfect month. And materializing subatomic world using woven fabric, woven cloth, I think. So I'm going to stop sharing the screen, my screen, because Isaac, you're going to introduce both Lindsay and myself, right?
Correct, yeah. So let's do it. Let's jump into this. So Lindsay Olson, like Maggie said, is going to start us off with a talk, The Art and Science of Ocean Acoustics. Lindsay's artistic practice grows out of an intense curiosity about the way our society is supported by science and technology. She has worked as Fermi National Accelerator's first artist in residence with the Metropolitan Water Reclamation District of Greater Chicago, the Field Museum, and other labs. Her current work grows out of 3-week research cruise with a RV endeavor with scientists using acoustics to study the ocean soundscape. Lindsay taught textiles at Columbia College, Chicago for over 20 years. When not visiting a lab or working in the studio, she can be found canoeing with her husband in one of Chicago's many area waterways. So Lindsay, you want to take it from here?
You have to introduce me.
Oh, you want me to do this now? Okay, sorry about that. And Maggie will join us with a talk on the journey knots, silk to hemp. Maggie Diversa, trained in textiles engineering, a bachelor's, material science, an MS, and social science, a PhD, and examines the connections between textiles and their agency from the foundation of technology. She spent over 30 years developing fiber forms for industrial and medical uses, eventually turning to the study of conditions of violent death in urban spaces, completing a doctorate in social science from Rutgers University. These distinct experiences, along with working in multiple countries and cultures, have convinced her that textiles also create all sorts of agency. She is currently working on knots and structures that tangle.
So today I want to invite you on an armchair voyage so that you can see what ocean science looks like and to make visible the invisible world of sound in the sea. So on a muggy day in June of 2018, after 2.5 weeks at sea, the ADN 2 crew and science team pulled into our last study site off the coast of Virginia. The weather was warm and overcast, the sea state was calm, and Dr. Mixus-Olds had just given the word to pop the lander, and all of us scanned the immediate vicinity searching for the orange floats attached to the hydrophone and data collection equipment. This 20-minute journey to the surface was a waiting game we had performed successfully 6 other times, sighting and retrieving the lander, downloading the data, and plunging the equipment back to the ocean floor to continue collecting data. But this time, as soon as Jen gave the word to release the lander, everything changed. The wind shifted, the sea state kicked up, a heavy rain drenched us, and a curtain of fog descended. And all of this made finding the equipment a huge challenge. This is science at sea, unpredictable, challenging, nerve-wracking, and exciting. I make art about science, and my work takes me out of the studio to places like this, a ship at sea for 3 weeks, where scientists worked round the clock to uncover the mysteries of the ocean ecosystem using acoustics, and I want to explain it using art. So how did a passionate science avoider like myself become inspired by scientific research? Earlier in my career, I had been painting idealized views of the Chicago area waterways, but I had been editing out the built environment. My husband and I are avid canoers, and one day when we were paddling on the Cal-Sag Channel, we passed this beautiful SEPA station. This engineered waterfall was built to add oxygen to the sluggish canal. The structure nagged at me, and finding out who built this structure and why led me to the world's largest wastewater treatment plant in Stickney, Illinois. After months of interviewing engineers, talking to scientists, attending workshops and lectures, I realized that I could learn enough engineering to create artwork that tells the real story of water in a dense urban area. And I know this is going to sound really strange, but I fell in love with science in the middle of this very wastewater treatment plant. So this is one of the pieces that I created. This is Carchesium. It's one of the microbes that's responsible for cleaning our wastewater. And who knew you could find such beautiful things in wastewater? So working on the wastewater treatment project gave me the courage to work on other science-based projects, and I'll save those stories for another time. But during a conversation I had with my son, Dr. Derek Olson, who also happens to be an ocean acoustician, he mentioned that a friend of his was organizing a trip on the Atlantic Ocean and was actually looking for an artist. How cool is that? So Derek introduced me to Dr. Jen Mixus-Olds, and my new project was born. So why use acoustics to study the marine environment? We humans are visual creatures, but at sea, light only penetrates a few hundred meters underwater. Visibility falls off dramatically in deeper water, so the kinds of visual observations that biologists use to study terrestrial ecosystems is not possible. Studying what's happening under the ocean requires a different approach. Ocean acoustics uses sound to describe what's happening in the ocean soundscape. The scientists on this project used both passive and active acoustics. This natural divide inspired me to create 2 large-scale textile pieces. Active acoustics uses sound to visualize what life forms inhabit the water column. A ping of sound is transmitted down from the ship, and those sounds collide with life forms that are in the water column. The returning echoes or sound waves help define the life forms found in that particular layer of the ocean. On the active acoustics artwork, I've included the echo sounder ping right here and the returning sound waves. And you can see that the sound from the ship comes down and looks kind of orderly, but once that sound wave bumps into life forms in the water column, everything looks a little bit disorganized. And the returning sound waves have a distinctive signature, and that unique signature helps researchers know what's going on. So one example of how active acoustics illuminates ocean life is how it describes a particularly dramatic event. The deep scattering layer is several meters below the surface, and it's a mix of tiny life forms, zooplankton, small fish, squids, and zooplankton and small fish are the foundation of the ocean food chain. But this means that they themselves are food for many predators. So they travel a daily migration route. So at sunset, all the zooplankton start migrating to the surface of the ocean. They feed all night, and then at dawn, they scoot back down into the depths. And this is actually a very useful strategy because there's no place to hide in the open ocean from predators. So here's a close-up of my stitch work representing this deep scattering layer. And these are the active acoustic equations used to understand the data. So here's an example of what the data actually looks like. So this is an echogram recorded by Dr. Warren's night crew, and you can see why I was inspired by images like this. And this is where the migration is happening. So it's about 6 p.m. here, and literally by like 6:50, almost 7 o'clock in the evening, that is where the zooplankton are hanging out. So here's what some of the zooplankton look like. These are some of the critters, they call them. That's their affectionate title for them. And before I move on to the passive acoustics information, I thought I would share a bit of my studio process with you. One source of inspiration was the tapestry-sized embroideries of Swiss artist Lissy Fun. Monumental embroideries like these are rare and labor-intensive, and her embroideries harken back to the medieval embroideries created as luxury wall hangings, but with a modernist sensibility. And before I left on the research cruise a couple of years ago, I had the opportunity to visit the Art Institute in Chicago to see this artist's work in person. The textile staff were kind enough to unroll her monumental work so that I could study them. So this slide gives you an idea of just how large these embroideries are. And after my talk, I'll drop in a few links to her work. There's a catalog of her work and a page on the Art Institute of Chicago. And Isaac is going to show us a few of her sketches, which will be really exciting. So here are a couple of my sketches developed in preparation for this project. I limited my palette to monochromatic tones in teal in both silk for the background and cotton threads used to stitch. And I limited the number of stitches that I used. Limiting the number of stitches in the surface allowed me to have a more unified look to the work. So most of the stitches I used on this piece were various kinds of couching, Bokhara, Romanian, and regular couching. I also used a bit of padded satin stitch and intentionally sloppy French knots. And I also used a wrapped back stitch for the equations because it was added some clarity. So I added a few beads for some visual interest as well. And here you can see some of the development of the equations and a little bit of a close-up of some of the stitch work. So I want to develop art that stands on its own, even if someone is not interested in the science. My aim is to pack as much science information into the work as I can, but in a beautiful way. My materials and techniques are as important to me as the scientific content. I knew early on that I wanted to work with silk de Biennial. This fabric has a pronounced grain line, and I exploited this characteristic so that the surface of the artwork would shimmer like the light on the surface of the ocean. Historically, heavily beaded and embroidered clothing would have been created as a sign of social status. By using these labor-intensive processes and materials, I'm creating a visual link that helps elevate the status of the science content I'm illuminating. The second part of this project captures the power of passive acoustics to advance our understanding of ocean ecology. Because of limited visibility, marine mammals and fish are highly adapted to producing and perceiving sound in the ocean. Passive acoustics uses underwater microphones called hydrophones to collect data. The equipment collects information in all directions and listens into marine life, including sounds generated by marine mammals, sounds of human activity like shipping, seismic activity, and what's called abiotic sounds like wind and waves and ice. I've interpreted the hydrophone data here using embroidery and beading. The ocean is a really noisy environment, and I've used an all-over stitch pattern to represent the ambient sound. The middle of the artwork is a stand-in for the equipment used to house the hydrophones. Here you can see data from the humpback whale in this area. This is shipping sounds right here. This is the seismic activity that was captured on one of the pieces of equipment. This is a mysterious set of data. Jen didn't know what that was. She thought it might be a school of fish, but it is for perhaps other future researchers to figure out exactly what all the data means. Still a lot of mysteries there. So how far can sound actually travel underwater? The ocean is divided into horizontal layers in which the speed of sound is influenced by temperature, warmer in the upper layers, and pressure in the lower layers. These shifting layers, the SOFAR channel, it's a horizontal sweet spot where low-frequency sound can travel great distances. Low-frequency whale song, like those of the humpback whale, can travel across the oceans. And one set of songs was recorded traveling between Florida and Nova Scotia. And I'd like to play with a small snippet of some of the hydrophone data that was collected. It is, however, from a really noisy site. It's got shipping sounds, humpback whale song, and you can even hear a few porpoises. So you have to listen carefully to separate out all those various sounds. Sounds so eerie. Anybody a fan of Star Trek 4? I'm going to drop in a link into chat when I'm finished speaking so that you can hear the Adion audio gallery, and you'll hear lots of other charismatic megafauna, as the scientists like to refer to marine mammals, and you can hear a lot of the sounds that are separated out. So as an artist, I'm always interested in what science looks like. I've worked with a number of scientists in terrestrial labs, but science at sea poses some unique challenges. And while preparing for my trip, I told my family and friends that I was going on a science cruise. And some people hearing the word science cruise imagined that science would look something like this. So no, there was really no room for lounge chairs. We all worked 12-hour shifts around the clock. We tried to squeeze in as much time in data collection as we possibly could. It's very expensive to go to sea for science. This was also the first time that I had an opportunity to participate in science, and it was really intense, it was rewarding, and it was really a great inspiration to making those pieces. So science at sea presents some unique challenges. For starters, heavy equipment is deployed and retrieved by cranes on a constantly rolling and heaving surface. Every member of our ship's complement needed to stay alert, and every time we stepped on the deck to accomplish a task, we needed to remember our safety training. I never forgot that the ocean is a hostile environment for human beings. But amidst our 12-hour shifts were moments of grace, like the time a pod of 125 dolphins greeted us at the Virginia study site. We also had magnificent dawns and sunsets. There are strict rules about what activities get to be defined as scientific. A scientist must be able to objectively look at the data without overlaying his or her own opinions and feelings so that she can examine the data empirically. But before an experiment begins and after the data is analyzed, there's plenty of room for connections between science and human experience. Art has the ability to connect us with our human nature, flawed, messy, and emotional. The goal of this project is to lure in science-phobic people with handsome art and blow their minds with cool science. Translating the science into textile art offered me a meaningful intersection for my studio practice. I've created art that celebrates science and informs the public about ocean research. So now I want others to understand what I've learned, that you don't need a PhD to fall in love with science. Thank you.
So I'm going to talk to you about a journey, and it's really one of knots, from silk to hemp. And first, I want to tell you how I started my affair with silk knots. Most of my career has been spent in looking at surgical knots, which really are, and silk is the gold standard for surgery. And so one day my boss came to me and said, I want you and your teams to create a suture, to design a suture that creates very secure knots, just like silk. But silk also has a problem. It has inflammation as it breaks down in the body, and that is not preferred. So the next slide is a little bit gory. So if you don't like gore, this might be the time to check your phones. But I do want to explain to you why we need such secure knots. This is a traumatic wound where you have to use both inside the tissue and on the skin very tight knots, and a lot of them, because otherwise you get openings where infection will come. And this is an incised knot, so it's not as critical that you have really tight skin knots, but you have to have really good fascia knots. So both wounds, while very different, require really secure knots, and silk's been used for ages. So what we did was to go back to a definition of a knot. And there's so many out there. But Clifford Ashley, who is known as the expert in knots, he's a sailor, he wrote the definitive book, some people tell me, on knots. He has a very simple one. It's any complication in a length of line. The internet has a bunch of different knots. A tangled mass, fastening of 2 lines of rope, something hard to solve, constriction, the base of a woody branch, the tree knot, and a closed curve. I would say closed curves in a 3-dimensional space. My definition is that it's a space where a line becomes tangled and tightly drawn together in security. So as we thought about what the requirements were for a secure knot, we had 4 major ones. One, we couldn't have any reactivity in vivo. That was really key, because as you see in this molecular structure, these double bonds are what really forced the reaction as the silk degraded in the body. So while the silk does have inflammatory reaction during in vivo degradation, we needed an inert material. Secondly, we needed something that had low bending rigidity, that was pretty flexible. And these, I'm talking about the filaments. We needed low abrasion. We needed something that had low in vivo mass, and we needed adequate filament mobility. Now, what I mean by that is that we needed the filaments to have freedom of motion, so that as they were manipulated, they would have places to stay. So an irregular cross-section, a non-uniform uniform length, micro deniers, it all led to better positionality and better area packing, because that's what silk is. We also needed high strength and flexibility. We needed very low shear strength, shearing strength when you just move across 2 surfaces, and low filament abrasion. So the helical angle, the angle that tells you how much twist you have in a yarn or in a full cable, and that's right here, that's really almost in our minds the likely, or at least in my mind, one of the most influential factors. And the longer your filament is, and if you have around a 10-degree helical angle, that's good. You also need a smooth surface to prevent tissue drag, especially in those traumatic wounds where you don't really know what you have in the tissue, and it does provide low trauma. Let me just go back here. I just want to talk a little bit more about this helical angle and some of the effects it has. This is a piece I'm working on right now, where this is a map of New Jersey, but backwards. It's the backside. And I needed to have a yarn that had really high coverage. But yarn that has high coverage has generally low twist and low strength and a lot of elongation. The modulus of a high twist yarn would allow it to really cling to other things, but I needed coverage first, and I had to compensate for it not having that ability to cohere. Then the next thing that is also problematic in the determination of how to build a really well-balanced cable are these colliding forces. As you can see in this cable, you have normal forces that are straight up, you have the radial, you have shearing forces right here, all along your filaments. And all of this is compounded once you knot it. So within the knot, you have more shearing forces, more radial, and you have further manipulated it so that you may lose strength. So when thinking about all of this, we did come up with what we thought was a winner. We changed the molecular structure to an inert material, it's glycolide and caprolactone. We really extruded something with a fine denier, 1 denier per filament, which is very fine. We optimized both our helical angle in here and our braid angle, and we had continuous filament lengths. And we coated each filament, and there were hundreds in here. We did that by a pressurized method of coating. So we met the key requirements, certainly of security, inertness, flexibility, strength, low filament abrasion, and high filament cohesion. So now what? I had left J&J and was planning on doing additional studies of knots with other natural materials, linen, hemp, wool. So I wanted to expand the study to one of how is the dimension moving, changing? How are the filaments moving? And I wanted to look at the moisture, the dye uptake, and the effect of dyes. But then COVID-19 happened and the lab closed. And I needed to do this with labs. So it was a little bit problematic. So I had to sit back and really think about the limitations of physical characteristics. And early in my career, I had to study entangled yarn. And this, people remind me as a boucle, I just would call it air entangled. And I learned with this, there are definitely limitations to physical data. This I could measure time and again, but these loops, you couldn't measure them. So I guesstimated all the time, but I knew I could rely on that. So in my thinking in these last few months, it just really came home to me. The physical data provides the basis of design requirements. It's unambiguous. Say a molecular structure, it provides little room for confusion. And it is the foundation of what something is, but it is not what it can become. So I had to take a turn on my journey. I went back to my definition of a knot. I thought hard about how things become tangled and how they're tightly drawn together for security. And I changed my questions. So how does a line become a knot? In other words, how does that cord get tied? And in the becoming of it, how does it change? What is the agency of the line and the knot? What does it do? How does a knot serve as evidence of security? And what kind of security? And these questions will rest on the presence of physical data, the foundation of it, but will not likely be fully answered by that kind of data. And as we all know, knots, there's so many different knots. So Isaac calls this my inspiration page, which is an apt term. There are a lot of different knots and different reasons for using them. These are wristbands, and this is special knot for fastening. These are different constructions of horse leashes, and I was playing around with just overhand knots. These are both decorative and line. Here's a beauty of a tree knot. This is another New Jersey piece I've done where I've used the Gordy's knot, and it was really stable. And this is the quipu, a variety of different types of knots used for counting. I think we all know about this. But in essence, there's just a lot of knots. And so I had to settle on something that has not really been studied, but falls into my thinking of agency and becoming. So I moved to Cordage. And Cordage is in the maritime industry. It was one of the enabling products that allowed ships to sail from England, from the colonies here to Africa, to the West Indies, because they needed thousands and thousands of feet and yards of cordage. So I decided to study the becoming of cordage, how it became, and the agency. And because I like boundaries, I am limiting it to the 16 and 1700s and in the Rhode Island and Massachusetts coast. Surprisingly, at least to me, these two states, especially Rhode Island, had the most slave ships along the coast of America in this era. And what I examined, I went up, I think this was the only thing that was open during COVID. I went up to Connecticut, I live in New Jersey. And I walked through the Mystic Seaport because they do have a rope walk. And what I also want to study is what were the conditions of this? But let me get into that later. So there's 3 buckets or 3 sections within this part of my journey. Here's some of what is already known, and I have to really continue on that. But most maritime cordage was made from hemp, cannabis sativa, a bast fiber. It's easy to grow. It doesn't require highly cultivated soils. And most of the hemp at that time was imported to both the US and to England from Eastern and Northern Europe. And the colonies here did subsidize the farmers to grow the hemp. And the reason it was so useful, it didn't have any of those double bonds as connectors. It was very inert to moisture. And you could make really long filament out of this fiber if you knew how to strip it correctly. So that's one section. The second one is I want to study how it became cordage. And there I do need both the technology of it and the conditions on who worked there. The bonded workers were there, slaves were in the rope fields, and what were the conditions for these to occur. This is a short rope field. It's 250 yards long, and it's in Mystic in Connecticut. But normal rope fields, which are all over Massachusetts and Rhode Island, are about 1,000 yards. That's a long way to walk with really heavy ropes. And this, they start from the creel, they go through the largest spinneret ever, and they go all the way down. And then the agency of cordage. These are miscellaneous ropes, but that are used all over the ships. And these are reproductions. And here's a rigging that allows the sailors to get up and hoist sails or adjust depending on the winds. And here is a netting. Now, in the 16 and 1700s, on both sides of a slave ship, you would have what is called a suicide net. And these nets were intended to catch those kidnapped Africans that wanted to jump either to safety or to their death. But as we all know, the captain of these ships was there to make a lot of money, and each person, each human that was captured was money to them. So they put netting on both sides so they could catch. And the technology of this netting, while it seems low tech, there needed to be a certain porosity or an opening here to not be too small so it wouldn't bounce, and not to be too large so it wouldn't sink. So within this torturous device, even technology reigns. Now I'm going to leave you with this slide. Sorry, it's really a simple slide, but it has complicated structures in it. It's part of a rigging. It's a coated hemp, coated with tar. And these cords act as connectors, act as lines to holding of a knot. And these act as both holding line, whoops, sorry guys, but also these were the steps that allowed the sailors to get up. But in doing this, you have some complex technology there with agency that was designed to be violent. And I will just leave it right there and move to introducing Heather, Isaac, and Elizabeth. Heather MacKenzie, who's going to talk about the meter, is an artist and educator with a practice founded in hand weaving. She has acted as a Fulbright Scholar in Paris, France, a Fountainhead Fellow in VCU in Richmond, and an artist in residence at the Icelandic Textile Center, Acre in Chicago, right, Heather? Mm-hmm. Mass MoCA, Cité des Arts in Paris, among others. Her work has been exhibited at venues including the Textile Center of Minnesota, Sediment Gallery in Richmond, Virginia, Heaven Gallery and Rona Hoffman Gallery in Chicago, and the Point Dôme in Toulouse, France. She received her MFA from the School of Art Institute of Chicago in Fiber and Material Studies, where she occasionally lectures, and her BA from Brown University in Rhode Island. Welcome, Heather.
Thank you.
And Isaac focuses on the care, preservation, and exhibition of objects as a conservator in textiles at the Art Institute of Chicago. He and Elizabeth are going to be talking about ghostly things, materializing subatomic world using woven cloth. Isaac maintains a research-based practice in art and science collaboration, specializing in textile technology with an emphasis on 3D woven structures. And he is a lecturer at the Department of Fiber and Material Studies at the School of Art Institute of Chicago. Isaac received his training in textiles and textiles conservation, studio art, material science, and technology across Chicago, Manchester in England, and Paris, France. He serves on the board of directors of the Textile Society of America and is a recent artist in residence at the Fermi National Accelerator Laboratory. Welcome, Isaac. And Elizabeth Pope, where are you, Elizabeth? I see your E. There you are. She is a specialist in the pre-Columbian Mesoamerican art, architecture, and ritual performance with a particular focus on the cosmology and cosmogony of the ancient Maya. She has trained as an anthropologist, archaeologist, and art historian with a BA in cross-cultural studies from Colgate University, an MA in archaeological studies from Yale University, and a PhD in art and art history at University of Texas, Austin. Her research seeks to understand the mythological beliefs of communities throughout the Americas within their distinct cultural and historical contexts, and to understand how different societies manifested the sacred realm in the historical world. I'll leave it with you, Heather.
Okay. Hi, everybody. Thanks for being here. As both Lindsay and Maggie started us off, I'm going to add another story that that comes to textiles a bit later on. This is mainly not a story about textiles, but it also is, because textiles are there. They're often in the background, often highly technical. They serve along a spectrum from symbolic to protective. This story is also a background, a foundation. It parallels the ubiquity of cloth. In my own pretty unconventional practice, I think through metrology, even as I think through the path, the twist, and the weight of each thread. So let's begin with a milestone moment for our planet on May 20th of 2019, less than a year and a half ago. There's irony to calling it milestone. This figure of speech refers us back to times when stones were placed along roadsides to mark the miles. But on this date in May, we redefined the kilogram, the international standard of mass according to SI, or Système International. That sphere, likely a decoy for the real thing, our heat, sweat, breath offer multitudes of material corruptions. This mirrored decoy represents as perfect a spherical crystal of silicon-14 as can be machined over a 30-year period. Its mass calibrated out to 8 decimal places to match le grand K, the prototype kilogram. After this calibration, they measured its volume, again to 8 decimal places, so that they could calculate the number of atoms in the sphere. And then the sphere became a relic. Perhaps it isn't a decoy, because after collecting and crystallizing a perfect sphere of silicon-14, calibrating its mass to the prototype kilogram to 8 decimal places, measuring its volume, again to 8 decimal places, it has served its full purpose. It doesn't require our protection. It can retire. It can age. It can even die. Its use then transforms into celebrity, sensation. Here, we are taking pictures of the people taking pictures of that sphere. The vault at the International Bureau of Weights and Measures in Sèvres, France. 3 separate keys open the door. Triple glass bell jar over the 39.17 millimeter right cylinder of PT-10IR. In this aged material prototype, we occupy the spacious uncertainty of 2 decimal places. What is a standard deviation? The bell jars attempt to shelter the kilogram from the ravages of time, yet the body continues to age. And over its 130-year lifetime, it has steadily lost weight. The meter is kept separately, and it retired decades ago. Made from the same platinum iridium alloy. Hard faces gravitationally sucked against hard faces. Air sucked out. The meter and the kilogram, sibling prototypes in intention and original definition, now siblings in their slow turn away from any material relationality, attachment, or meaning. Finally, they are both retired. 3 white men. Are they collaborators? Did they choose to be? One is clean-shaven. One sports a trim goatee, absent mustache. One wears a similarly trimmed full mustache and beard. Netted head hairs, gray beard hairs, blonde arm hairs. They have an ease with one another. They seem to feel differently about physical touch than I do at present. Forearms rest against one another. Left arm, right arm, all upturned. Tattooed on the soft inside with the same text. À tous les temps, à tous les peuples. For all time, for all people. Planck's constant to 8 decimal points. Marianne appears in 2 of the 3 tattoos. Here she's on the left. Symbol of liberty, fraternity, and equality of the French Republic. She's dressed in Roman-style garb with a Phrygian cap, right breast bare. She holds a meter in her right hand and a kilogram in her left. 3 sibling prototypes, Marianne, the meter, and the kilogram. How is a sibling forged? Who is a collaborator? Can we choose? 8 decimal places. This degree of precision means that a satellite orbiting the Earth in our exosphere can map the position of my phone to within a few feet of its location. This is extremely precise. Let me tell you what this precision means to the body, if I can. A woodworker might perceive the difference of 1/64th of an inch or a little less than half a millimeter. This is about the thickness of 2 pages of standard printer paper. In order to carry this embodied metric out all the way to 8 decimal places, My base unit of measure must be more than 1,000 kilometers long. France measures about 1,200 kilometers from north to south. How can I comprehend measuring France to within 2 printer pages of precision? I don't believe that I can embody this degree of accuracy, meaning I cannot relate it to my body. And yet, the meter was touted as the people's measure, accessible, universal, free. Here is an early educational billboard, a bronze meter installed in marble in 1799, still on display outside of the French Senate in Paris. Conceived of under Louis XVI and realized under Napoleon during the French Revolution, the metric system was the product of the late Industrial Revolution. It embodied Enlightenment ideals of rational thought borrowed from ancient Greek philosophy, logic, and mathematics. No wonder the metric system also borrowed from the Greeks for its name, even though its decimal logic traces back to Arabic mathematicians from the 12th century. Material prototypes from the metric system's early history are displayed at the Musée des Arts et Métiers in Paris. Octagonal case for the kilogram with velvet rest. Long, narrow case for the simple meter bar, velvet lined. So much platinum. Subtle ostentation of velvet. Here, the velvet does not serve the prototypes it cradles. It serves my eye. It allows me to discern softness, richness, finery, signifiers of care, of class, of comfort, of antiquity, of authority. Napoleon loved the metric system with a similar fervor as he loved the Jacquard loom. He had an eye for technologies that could centralize power. He had an eye for efficiencies. He was not interested in power that related to personal agency, skill, or to the haptic knowledge of the weaver. Here's a detail from a portrait woven of Joseph Jacquard, created in around 1840 on the Jacquard loom, just a few years after weavers staged massive strikes in Lyon because they were losing their jobs. This portrait required 24,000 cards to be punched and strung together in order, where each card described the path of a single silk weft inserted perpendicularly to the warp threads. The full portrait is about 85 centimeters tall. I take my calculator and my computer for granted when I need to find aspect ratios, when I need to adjust a design in Photoshop. Imagine if I punched all those cards and then I found I'd stretched out my perspective. I digress. Here Jacquard sits, an inventor of a small part of a large machine that now bears his name, staring out smilelessly from this weaving. In his right hand, he holds a compass, a symbol of Greek geometry, and more generally, a symbol of the human ability to learn about the world around us. Here again, we revisit this medallion cast in 1839 that commemorates the metric system. Opposite Marianne, in her robes and cap, an unclad angel casually measures a quarter of the globe. They use a compass quite queerly. This is not how a compass works, according to standard mathematical conventions, but like the kilogram, lit by cold blue LEDs, or the compass as prop in Jacquard's portrait. Here in the guise of a geometer's tool, we have a symbol of power and conquest. In 2016, I measured a number of Confederate monuments in Richmond, Virginia, while I lived there. I'd learned to read their gestures in some basic ways. A figure facing north had died. A raised hoof meant death in battle. But after a few months there, I, a white northerner, learned to normalize these monuments looming around me. Measuring was one way I could understand their physical shape and the space that they occupied. Ownership through measurement. I used a 100-meter tape measure that I wove on a TC1 loom, double-faced, with inches demarcated on one side and centimeters on the other. Calibrated periodically, this tape measure is more a record of my own inconsistent labors than it is an authoritative rule. Soft, like a tailor's measure to touch the body. Every inch varies from the next. It is consistent only to itself in the relationship it holds between each inch and centimeter, and in the number of threads packed between demarcations. The intersection around the statue of Robert E. Lee on Monument Ave was under construction at the time of my measuring. I felt conspicuous with my notebook and no orange safety vest. The wind kept blowing my tape measure around. A Black construction worker noticed me and helped me by holding the tape measure at its end. He didn't ask me what I was doing there, measuring those granite slabs with that flimsy, unraveling tool. We talked about art. He told me he liked to draw at school, but that wasn't going to pay the bills. I still can't disagree with him. We construct meaning in our world. Here, a tailor's tape measure might measure some massive body. Its conventional job to translate between the material world and other calculus. Instead, it is put to a queer use. Its job is not to occupy space, and yet here it does just that. Still working between the material and the abstract worlds. A square and a rectangle pinned to a wall become a flag. Hand weaving is often relegated to the decorative arts. It can be seen as tedious, old-fashioned, perhaps even nostalgic. A minority of weavers insist on its politics, insist on seeing it through another lens. What are the meanings that the majority of us dismiss? The histories and the power? Can we reclaim this, and what does it look like when we do? Who will pay attention? I want to read a short amount from a collaborative duo that I'm involved in with Kate O'Brien called Weave Thing. To labor together is fundamental to all creative acts. Our work as artists relies on a deep sympathy with the materials and tools of our practice. This kind of collaboration and attunement is tightly aligned with an engineer's understanding of a material's properties and the technician's savvy in tinkering with her tools. We encounter the loom as a problem space where we work to expand what textile is. Every loom vibrates with possibility made manifest in new relationships with other machines, ears, eyes, computers, weights, wrenches, rigs. As artists, we invest differently in process, method, and knowledge creation. The tacit and fearless subjectivity of our production is often off limits to a scientific researcher. Difference in technical expertise and approach can lead to generous and generative questions, conversations, and insights. Reciprocity and mutual respect fuel the exchange, mutation, and entangled growth of new skills, sensitivities, interests, and expertise. We take the technical history of our tools very seriously. This lineage becomes a set of archetypes and standards, each standard shaping its own set of axioms or assumptions about the possibilities of what can be woven. But these parameters also give way to the sensual and dynamic nature of cloth, yielding unpredictable results. In our work, we debate the best ways to squish a platonic solid or draw in the fourth dimension. We invent elaborate drafting notation for multi-layered weave structures and mathematical propositions to engage weavers across the practice in new ways. and we dream about tapestry looms that manipulate non-Euclidean geometries and interventions into the TC2 that distort the rectilinear plane. Our objective is to expose and expand our collective sense of what weaving can do. Thank you.
Pardon. I want to show you a couple of projects that I have that are long-term projects and definitely in progress. So what you're looking at the moment is in the background is a time-lapse video that was created by my collaborator, Benedict Diemer, NASA Einstein Fellow and Assistant Professor in the Department of Astronomy at the University of Maryland now, and his colleague, Phillips Mansfield. And it is the focus of our project, The Fabric of the Universe, exploring the cosmic web in three-dimensional woven textiles. It's a simulation of the collapse of dark matter in the universe in billions of years. And you can see the time lapse at the top right-hand corner. Just to give you an idea of scale, this is what we're looking at. We're talking about extremely large distances and extremely long periods of time to visualize the invisible and to give us some understanding of the world around us. Benedict specializes in the computational astrophysics, meaning that he runs and analyzes large computer simulations. The research interest is in structure formation and gravitational collapse of matter in the universe into the structure that we observe, that we refer to today, such as galaxies and dark matter halos. What you see here is a billion dark matter particles in the simulation that are affected by gravity, and the time-lapse video, the collapse of the billion dark matter particles over the 13.9 billion years. The lighter areas are the denser areas of dark matter, the darker voids. The halos are the white dense areas of this image. Our galaxy would be embedded deep in one of these halos. In the simulation, the halos are highlighted to identify their location and their size. We can zoom in and zoom in further to continue to see detail of what this would look like. Benedict would describe this filamentary with characteristics of sheerness, opacities, and nodes, common terms that we would use to describe textiles. And finding a common language has been key in making connections across our very different fields. One of the most interesting things about this visual is that there is no perspective here. This is a slice of the universe as it is read on your computer screen. There is no up, there is no down, there's no left or right. It's just relative to your location on Earth. And that's irrelevant here in this image. Because Benedict sees numbers when he looks at this image. I see filaments, fiber, weaving, and 3D space. So we had to figure out ways to be able to speak to each other and be able to understand this, this image, these simulations into 3D space for a weaver especially. So he began to explore this cosmic web structure in a three-dimensional space. You could see a simulation image of this that was simplified, where he's identifying halo structures in a spherical form, because that's the shape that they take in different sizes, and their filamentary structure simplified to see their connection in a given space. We continue to work with this idea to understand the cosmic web in this 3D space and try to understand what that physical form would look like if you would look at it in the round. So it's simplified, but also in that process, we're connecting those particles to create walls and give shape and to create something like this that will be 3D printed. This is one of our first 3D samples, 3D printed samples in that is about 25 centimeters cubed. But what is data to a weaver? And I don't have to explain that to anyone here. You can see the links to binary code and the links to computing. In my interest, I very much want to explore depth in cloth. And in this particular case, I'm exploring stacking of layers to create depth. In this early sample that I'm showing here, there is a stacking of 64 layers of weft, splitting the warp into the 64 layers, so approximately 13 to 14 warps per layer. So these layers are not functional cloth by any means, but they are separate layers regardless. In here, I am beginning to explore shaping of that stacking so that we could explore creating that spherical structure of a cosmic web halo. This is an example of a quarter sphere with approximately 100 layers of cloth in the center. This sample, I should also say, was woven in a hand-operated Jacquard loom at TC1. And having that control was also really important, that hand control. We also explored creating these spherical shapes using columns and rows. And with that also giving us differential tension, which also created that spherical rounded shape that you could see at the top here. And that data looking something like this, a weave draft, all pixelated, using to be able to weave this on a conventional Jacquard weaving machine. We wove this at the Textile lab in the Netherlands. This is the first installation, one of the first installations, I should say, that was installed at the Planetarium in Chicago. It is showing a region of 26 halo structures woven on a Dornier Jacquard weaving machine, like I said, in Tilburg, the Netherlands. The cloth overhead is mounted on frames to reflect backstrap looms. You could see that in the details on the sides. To really lay out that narrative of weaving, giving rise to modern technology and supercomputers that we use today to simulate the creation of the universe, such as in Benedict's work. At the bottom is weighted with porcelain loom weights to give the vertical tension. Where the warp, the white warp intersects the black weft are the spherical structures. You can see that here, the difference in the black and the white. Those intersection points are where the halo structures are located within a 4-meter cubed space. So this project led me to connect with the folks at the Fermi National Accelerator Laboratory, AKA the Fermi Lab. They are the US flagship particle physics laboratory located just outside Chicago, where they do research in some of the most fundamental scientific questions. Big unanswered questions of science, such as how did the universe come into existence and why their laws of nature are the way that they are. The building that I showed you there is Robert Bolton Hall, the center of Fermi Lab. and also known as the Cathedral of Science. And I was really fascinated by it being called the Cathedral of Science. It's the center and where many brilliant minds from all over the world come to do work in particle physics. They're not only in theoretical physics, particle physics, cosmology, and also includes an arts program as part of their outreach and engagement. And this is how I was able to get involved. Fermilab has built a world-leading infrastructure to study the behavior of neutrinos, one of their main focus there. And what is a neutrino? Well, breaking down the world into the smallest possible parts and is what's known as the elementary or fundamental particles. 12 of them, smaller particles, quarks, leptons, and the smaller building blocks of the cosmos, and 3 of them are neutrinos, identified here by the Greek letter nu. Neutrinos are fundamental particles, which means that like quarks and photons and electrons, they cannot be broken down into any smaller bits. Neutrinos, of all particles with mass, our neutrinos are the most abundant in nature. They are also some of the least interactive. Roughly 1,000 trillion of them pass harmlessly through your body at every second. Neutrinos created in many processes in nature. They are produced in nuclear reactions in the sun, particle decay on Earth, and explosion of stars. They are also produced by particle accelerators and in nuclear power plants. Neutrinos come in 3 types called flavors. One of the strangest aspects of neutrinos is that they don't pick just one flavor and stick to it. They oscillate between all 3. They are elusive. Neutrinos are difficult, but not impossible to catch. And scientists have developed many different types of particle detectors to study them. Fermilab has about a dozen different neutrino experiments composed of neutrino detectors, such as you can see here, mini boon, micro boon. I think you also saw Icarus pop in one of these images, all exploring different aspects, including how they can change their identity. The DUNE, the deep underground neutrino experiment, which you see here, is one that will shoot a neutrino beam through the Earth to a huge detector in South Dakota. And Fermilab is an open laboratory, and I've been able to visit many of these different facilities. In fact, I was always taken back at how open everyone was to share their work. And I'm always one to say that, we should all know about the important work that they're doing here. At many of these facilities and their control rooms were monitors showing what was being detected in these big detectors that you saw. And many times cosmic rays and other noise and some neutrino events. These monitors were like the looking glass into visualizing the invisible within each of these structures. The one-on-one time and behind the scenes aspects were really moving and understanding this world at Fermilab, and I wanted to do the same for them. So I did. In partnership with some close colleagues at the Art Institute of Chicago, we organized a full day behind the scenes work to give a group of about 30 Fermilab scientists and staff an insight into our work in the scientific study of objects in our collection. Starting with my colleagues, Kathleen Kiefer, who you see on the left, in our work in textiles conservation, and also an introduction to textile technology using our collection. We have this mini Jacquard loom that people were very fascinated by. And also on the right, you see an introduction on weave drafts and weaving. We also gave them some introduction to fiber analysis, such as this spider silk fragment of the golden orb spider, excuse me. Sybil Tom, objects conservator, discussed her treatment approach of this seated Guayan polychrome sculpture. And in the galleries, a tour with our friend Elizabeth Pope in examining creation stories of non-Western cultures. And I really love this image here on the right because it not only shows Elizabeth, myself, and Lindsay, but just really how fascinated and engaged everyone was during this visit, because it started from the very opening minute of the museum hours till the very closing time, and everyone was quite engaged in everything that we had to say about objects in the collection. I tell you all of this intentionally because this interpersonal experience, this human experience, was actually the most influential in this project thus far. In the Textiles galleries, we prepared an exhibition on Andean textiles, supernatural textiles of the Andes that you see here. That was co-curated by Elizabeth Pope and Erica Warren. It walked us through the sophisticated textile technologies used in these cultures, the use and meaning of these materials. Everyone was captivated and very engaged at every little aspect of our descriptions and tour. This object caught our eye and really spoke to me while we were all together. It's a napkin fragment that Elizabeth will tell us a little bit more about. It's a discontinuous warp and weft technique that we'll look a little closer. But something that really stood out to me in this object is that I saw movement within the design, a pixelated movement. And I wanted to continue exploring that, especially in the presence of these 30 friends from Fermilab. It spoke to me of neutrino events and neutrino oscillation and vertical direction, in horizontal and diagonal direction. And in all directions, really. The geometry also lent itself to depict the fourth neutrino, a sterile neutrino that is also in discussion among scientists at Fermilab. So this is what I saw when we were together. I saw a pixelated visualization of what I had experienced seeing at Fermilab inside of these detectors. And being that I don't have access to the weaving equipment that I typically use, including my own loom that is currently at Fermilab, I quickly ran with the idea of just weaving with what I could. I believe also this idea of using a pin surface is also something that Jim Bassler, artist Jim Bassler, who's very beloved by TSA members, also used in exploring the scaffold weaving. And here's another fragment of what that is looking like, continually growing as I continue doing this. And the initial idea was that I would create a large hanging in the space above the art gallery that would be in a way similar of the 3D woven structure of the cosmic web that you saw earlier, but perhaps include this geometry and also depict these particle detectors. I've explored this, but weaving with this new method of hand weaving that is a new approach to me. I'm taking a different aspect of how this might look overhead. And although I will not be weaving this entirely by hand for this type of scale, it is something that I want to continue aiming towards as I continue to build on this work. And so I want to bring your attention to another program that we hope to have on the 14th of November, where Elizabeth Pope, who just popped up, will share more of her work along with more detail on the Cosmic Web project that I shared with you earlier. And what we'll do from here is I want to jump into some close looking while Elizabeth jumps on.
So good afternoon, everyone. It's a real pleasure to work with Isaac and the whole team here this evening. We want to open up the question and answers so anyone can respond to any of our speakers today. Please put in your questions or inquiries for anyone in the Q&A, and we're going to be responding to that. However, as we all appreciate close looking and really understanding individual works of art, to try to understand them in the context in which they were made, trying to get closer to the maker, their intent. I wanted to take just a brief opportunity to first of all talk about the textile that inspired Isaac and his ideas and contemplation about neutrinos. So again, we're going to open up questions and answer the Q&A, and also we're going to be looking at not only this individual Nazca textile, but we've got some really beautiful samples that Lizzie Funk had created that inspired Lindsay. So we just want you to be able to experience the works of art in person up close, and you can see Isaac is in the AIC lab with this very specific textile. And let me just give you some highlights, because we really don't have much time, and we want to make sure that there's a dialogue and a discussion in response to the presentations you've heard today. So this textile was made by the Nazca from South Coast Peru, probably about 300 to 500 AD. The Nazca people are widely known for the lines that are drawn on their desert plains. I should point out that just today, a new discovery of a new Nazca line image of a feline was discussed, although they think it's actually earlier than the Nazca. Now, throughout the Andes, textiles were the main form of artistic expression and the primary means of communication for all of the area's very diverse cultures. And this communication took place through the motifs and designs carried by the cloth itself, as well as the weaving structure. So this is just a little fragment. It only measures about 20 inches by 12 inches on the short side. And you can see it's actually mounted on this taupe cloth to help stabilize it. But what you see is the vibrant colors of the original weaving. It's made of camelid wool and cotton fiber. And one of the wonderful things are all of these colors. 14 distinct colors, have been identified for this single fragment, including 3 sets of plied fiber where 2 different colors are plied together to make a third. Now, I should just point out that no testing has been done either to the fibers or to the colorants, and perhaps that's something that our Art Institute scientists can explore in the future. Now, the motifs are quite interesting. This fragment has over 20 interlocking step frets. They're organized in a series of columns and horizontal rows that define the top and bottom. Now, the significance of this motif is not clear. It appears in so many different contexts, not only within the Andes, but worldwide. Some scholars have suggested this interlocking step fret reveals issues of symmetry and balance and the overall cosmic design, but we truly do not know. Of particular note about this is the structure that the weaving was done itself. Superficially, it looks like a plain weave. However, it was woven using a complex and highly involved technique that is only known from South America, and particularly from the Andean region. This technique is called a scaffold weave or discontinuous warp and weft. Now, unlike traditional textiles, neither the warp nor the wefts extend through the entire width or depth height of the cloth. Instead, each of the color areas was woven separately, supported by scaffold threads. So if Isaac, if you can hear me, maybe zoom in close to that juncture between two different color areas, because in each color area would have been woven as if a separate textile. And the warp and weft color both contribute to its color area. And the interlocking of the warp and weft of the adjacent color area is what holds the full piece together. But during the weaving process, scaffolding, whether it was thread or perhaps some kind of stick, or in Isaac's example, using individual needles to hold on to each of the individual units until all of them are interlocked and those scaffoldings can be removed. It's been suggested that this particular type of weaving is a ritual cloth due to the time and labor and complexity it is to weave something that superficially looks simple, but is actually quite complex. And some have suggested this balancing of warp and weft and the interlocking of the structure, again, reveals more fundamental ideas about cosmology with the balancing of opposites and complementary elements. So that I think is what we want to focus on just for the Nazca textile. But Isaac, would you like to turn over to look at some of these wonderful works by Lizzie Funk that you've also pulled for us?
Yeah, I think we should have Lindsay jump in.
Yeah, Lindsay, why don't you unmute and talk about the inspiration you get from these works and what caught your eye in your own?
So, you know, her finished tapestries are amazing and they're wonderful. But what really interested me was these tiny sketches that she did. And these works, yeah, what's the measurement on them, Isaac? It's like 12 by 12 or something?
They're pretty tiny.
They're pretty tiny.
This is like about 6 inches squared.
And you know, when Lizzie Funk used a padded satin stitch, normally what padded satin stitch, when you construct a padded satin stitch, you do satin stitch in one direction, and then you do a second layer right on top of it, slightly larger outside its boundaries in a different direction. But what Lizzie Funk did was she kind of used stitches to like corral raw fibers. So she would oftentimes have linen fibers that were, of course, this is a whole sample of undyed linen. And you can see where she's got some interlacing right in here. So she's like couching, but kind of satin stitching here. This is 2 layers of satin stitch. And I really like how on the sample, if you move up a little bit, Isaac, yeah, right here. Good, perfect, right there. You can see how she's got some raw fibers underneath, and then she starts doing this, not quite a satin stitch, but kind of a parallel stitching to tack down those raw fibers. And you can see on the back, if you move a little bit to the top of this sample, it looks like a horsehair ponytail or something. So here she is taking the raw fiber and wrapping it and allowing herself to explore the textured possibilities of not only thread, but raw fiber. And I just thought that was so interesting. And this tiny little dot with a hole in the middle, this is her working on 3D constructions. And I was fascinated by her ability to take the thread into 3D in such creative ways. It's a great sample. I think she even has some gold work. Yeah, is that the one with gold work?
Yes, it is.
Okay, so if you look really close, she's doing a little bit of needle weaving, stitching, changing stitch direction. I wondered if I can't remember because it was been like a while since I've seen them in person, but it almost looked like she was removing weft threads and replacing the weft threads with embroidery floss. And it's just
That's a good point. Yeah. that does kind of look like that, especially here. I think she's also maybe not necessarily moving it or removing it, but rather you could see that um, behind this area here, the warp or weft, whatever the vertical element is here, being gathered. It's just being gathered behind it. But it does give the illusion that it's maybe removed. It's just creating a little open work.
Right. So really, she allowed herself to do a lot of exploration in her sketches so that when she scaled up these embroideries to like giant wall hangings, she really had a lot of confidence in her technique. And if you look in this book, I linked it in chat. You can see that in her atelier, she did not work on a large frame. She had 7 or 8 embroiderers working on hoops, and the work itself was hung from the ceiling while they each worked on their individual sections. It's really pretty fascinating.
Wonderful. I'm glad we got to look at this. This is what the beautiful thing about working with objects, you know, and being in the lab. We're going to be working on these.
So I can start with, there's been a question, this panel has been fascinating this is for you, Elizabeth and Isaac. Are the units of the Nazca shapes all the same? Could they be using a pin loom to make those shapes?
Isaac, do you want to start?
I didn't catch the question, and I don't see it in the queue.
It's the last one. So you guys are fascinating. And are the units of the Nazca shape all the same? Could they be using a pin loom to make those shapes?
It's a really wonderful question and an interesting question. The weavers, the makers, and particularly of the ancient Andes, were doing things that even modern weavers and scientists are perplexed by. And this technique of the discontinuous warp and weft is one of those. The tradition of weaving using this technique still continues. It's actually being revitalized intentionally in an area in highland Peru, but it's still in existence. And the weavers in different communities have different ways of setting up their loom. Sometimes they will do a ground loom with 4 stakes to the ground. There's also backstrap looming. I believe it's in the National Museum of, it's not science, forgive me. There's a museum that has a fragment of a discontinuous warp and weft piece that you still can see the thread that was used as scaffolding. So that one example shows that they at least use scaffolding, but today sometimes sticks are also used. So what that scaffolding is, since it gets removed, we don't know for sure. And it's a wonderful question to answer. Isaac, since you look so close, what do you feel?
Well, I don't know that they would have used pins. I believe the literature or the experts that on how it would have been woven. I think this approach was a practical one, I know for myself, and then also what I know of, I think it was, I mentioned Jim Bassler. It would be interesting to talk to him about why he did that approach also. I believe he used T-pens for his piece. I want to also point out that Elena made a comment that Nazca Textile, just to note that some weavings with discontinuous warp and weft have been found in archaeological contexts in Mexico, which is, I don't know, Elena, if you are also mentioning a similar kind of design motif, but I know that in conversations with Elizabeth, just that motif itself is cross-cultural from where this originates, this particular piece, and also in Mexico and other areas. So that's definitely something to explore.
And as Elena pointed out, I hadn't heard that they had found this technique in Mexico, which is fascinating because for a very long time, they only thought it was in the Andes, but they've made discoveries in Chile and Colombia. So it's incredible to think of this and it really is an incredibly complex, takes a lot of time to set up and plan and then also execute. So that's pretty phenomenal. And ancient Andean textile studies, there's the comment that the weavers do extremely difficult things to get what looks like a very straightforward design and pattern. So there's a real expertise throughout these different communities working in ways that are quite spectacular.
So Vita is telling us that Catherine Ellis, who I think is on this webinar, she taught a workshop on this scaffold weave and developed a simple loom that everyone wove on.
Wonderful, yeah.
So yeah, that would be good to talk with Catherine.
And also she should reach out to the Andean textile experts who are working, Elena being one of them, of many, because that's one of the great questions and responds to something that Andrew Hamilton was talking about yesterday, and about getting to work your hands on to really try to understand and figure out how things could have been done. I think that's a really great source of information.
So another question, this is for Lindsay. Vita loved the presentations and had a question for Lindsay. She was particularly impressed with Lindsay Olson's thoughtful, poetic performance. And although she realizes it was a performance, she is wondering what you did, Lindsay, with the data post measuring the sculpture.
Maggie, I think that was for Heather.
I think it's actually, yeah.
For Heather.
I think it was
Heather.
for me.
Okay, for Heather.
Although Lindsay, you were as poetic as well.
Okay, to one of the two poets here, poetesses here, will it be a next step, Heather?
So, I mean, it's an interesting, there wasn't a next step at the time. It really was a performative act. I have been thinking about it recently because one of the sculptures that is probably coming down this month in Richmond is that Robert E. Lee statue. And if you look for pictures of it in the news, it's covered in graffiti right now. So it is, it's interesting having a record of my own interpretation of the size of the sculpture, and then knowing that those numbers will actually outlive the statue itself. So I think it has resurfaced in my mind, but I don't know exactly what I would do with it yet.
Maggie, I see a question here for you from Loretta Crippen. Maggie, does the spider silk work when, or will you cover that in the future?
So I've really only worked with silkworms, and so I haven't done much work with spider silk. It's a lot more difficult to use, and so I have not done that.
And then what about
the modulus?
Yeah.
Yeah, the modulus, I had showed a modulus curve on both the low twist and the high twist. Perhaps, Loretta, you could be a little, just let me know what detail about the modulus you meant, or we could take it offline.
Maybe she'll weigh in as we continue. Let's see. I think somebody asked another question for Elizabeth, actually, about whether the shapes in the Naskin piece, if they were symmetrical. And I think from my own observations, they're not. They look very free-handed. Yeah.
Yes. Definitely freehand, and you can see there are sort of 3 columns, shall we say, and then the 4th column is definitely at a larger scale than the other ones. So definitely very different hand done.
I'm wondering if everyone could go back and talk a little bit about the human experience in your projects. All of us mentioned that human experience and human connection in doing these projects. And because I mean, just knowing all of us here, there's clearly a lot of dedication in the work that we're doing and the way that we work. And I wonder if, Lindsay, you talked about this. Heather, you also talked about this. And also not only human experience, but the human touch in your talk, which I kind of just found fascinating as I was listening to all of us. And I wondered if anybody could expand on that and the aspects of your work and working in cross-field, cross-institutions. You know, Lindsay, it's always so fascinating how you connect with people or scientists from other realms. It just kind of happens. Every day I see you, you have another collaboration happening, and I don't know how you make it happen.
I've been very lucky.
Yeah.
Been very lucky. But yeah, I'll talk a little bit about that. It's really difficult working across academic disciplines because I'm really coming in from a position of a non-scientist. And so there's a lot of fumbling around in the beginning. And I think what has really opened this up for me is the ability to shift between art making and science learning. And when I get stuck in the science, I go back to the studio work. When I get stuck in the studio practice, I switch over to learning science. And I think it's this switching modalities that has been really, really rich. And also, you know, it's just impossible not to be inspired by a situation where you have a full immersion activity. Like being on board for 3 weeks was an incredibly intense experience. And it was really, I think I slept like 10 hours a day for a week. When I got back, I was so exhausted. But it was also magnificent. It was exhilarating. And it was great to be around people who are so passionate. And I'm sure all of you have had experiences too, where you're working in collaboration and it's the excitement is kind of infectious. Isaac, maybe you want to talk a little bit about that.
Well, I mean, I guess it's on my mind also because I think one of the points that I was trying to make is that, you know, I had a lot of different plans as to what I expected my outcome to be while working at Fermilab, and the way that, you know, lots of things that we can't control were in the mix. But that particular event that you were part of, and actually, Elizabeth, you were part of too, at the Art Institute, was actually quite fundamental in the way that we proceeded. And we actually still talk about that visit here, and about how successful and inspiring it was to all of us. And so I kind of feel grateful that that happened in many ways, because there's the human side to scientists as well as also the human side that we are always exploring as makers, or even in analyzing, learning about objects as we do in our work here, Elizabeth. And, yeah.
And if I can sort of follow up on that, I did my graduate work with Linda Sheely, and she was big into understanding Maya cosmos. That was one of her many claim to fames. And she was very interested in how to talk about cosmology and cosmogony and science to the general public. And before her death, she was actually working with NASA about how to talk about these great fundamental questions about who we are and where we live. And just studying, for me, the Maya in particular and other indigenous cultures throughout the Americas, it's interesting and I think important to hear how other cultures, other communities, how do they talk about these big questions of science, and share them with their publics. So I think that, and spending the day with the Fermi scientists was phenomenal. So I was telling them the cosmology of the ancient Maya, and it was as the ancient Maya represented it in their works of art and in their hieroglyphic text. So it was a really lovely, it was a lovely day and a lovely group to come and visit.
Isaac, there's a couple more questions. If you don't mind, maybe, if we go back to one for Heather from Vita again. She cannot help but continue to think about Duchamp's artwork 5, Standard Stoppages, in reflection of Heather's presentation, and especially in relation to measuring the sculptor. This is a very different era, but perhaps his questioning of how things are measured relates. Any comment?
Yeah, I mean, I think that I absolutely, I love Duchamp's piece, 5 standard stoppages as well. And we are, it is interesting trying to bring that into like to the place where we are at right now. I don't know if I have, I don't know if I can do that in this moment. Yeah, I mean, I think in terms of measuring the sculpture, and in this, both in, you know, in this political moment, in the pandemic that we're involved in, thinking about these monuments that we have grown up around, I am also thinking about my own personal agency and my own ability to own and mediate the space that I am inside of, and knowing my neighbors, recognizing the people around me, and I'm also digging into what measurement can be. I think it can be. It isn't just a number. So yeah, I think I could spin off in a bunch of different directions, but yeah, and I probably will. So thank you.
I saw a question. I'm sorry, go ahead, Maggie. You go
There's
first.
a question here on how do you develop your research questions, or do they emerge intuitively? And that's a broad question that also for me touches on the human piece, the human touch, where they do develop intuitively, but then there's always this formulation of how to develop research questions. But they first, for me, emerge from talking to people, from watching what they do, especially as, you know, I spend a lot of time in China. I would just sit and watch surgeons, and then the questions would emerge, and then additional questions would emerge. So for me, it was the human touch and the observation of what is going on as it is occurring. As I turn my journey to looking at Cordage, it still is working with people and talking and watching and observing, and then writing, and then coming out with the more focused questions.
You know, when I first started my project with Benedict, there's something that I remember we said to each other very, very, well, maybe on the first day, actually, that I kind of stick with and carry, is that we want to make sure that whatever we're doing in this project or collaboration has to influence and grow our own work, meaning whatever he's doing with me should somehow also advance his own research, and me the same. So when I'm thinking of weaving or making these structures, you know, I'm developing questions as far as to how am I approaching this in developing, growing this inquiry into 3D weaving or Jacquard technology. Like what is the next step that this could develop in the work that I'm doing. So I guess that's part of my own approach. You know, with this new thing that is happening with Fermilab, with this new this continuous warp and weft weaving, I'm still exploring what that might be and excited about it, because it's definitely a new approach. But
so we have, let me see how many more minutes. They're going to give us a hard stop. They're just going to cut us off at 5:45.
Okay, we still have a little time.
Yep, we do. So people are wanting to know how to get in touch with us. We are going to put on the website for TSA the announcement for the next session on November 14th, as Isaac had shown. And we would love to see, all right, email at us at either one of those. Thanks, Isaac. Okay, keep going with the questions.
Oh, we have a former Fermilab scientist, that it looks like, in the audience.
Maria Cecilia Holt is asking that, are there any thoughts now about textiles and disease/virus, the wastewater and the virus, or equations and the virus?
I will talk about the wastewater. This is a
Okay.
relatively new area in wastewater treatment where they're looking for disease, amounts of disease that are carried in the wastewater. And so I think the pandemic has been offered a perfect opportunity to start experimental trials of trying to identify the rise and fall of a general population's disease. This is pretty fascinating. So somebody else can jump in.
I haven't really thought about it, but it's a really interesting concept, especially around the disease and textiles and how a textile, because people are sometimes saying that there's some droplets that stay on textiles, but maybe more than that. I mean, there's something about masks and disease. I mean, there's quite a bit there. So I think that's a really interesting topic.
Yeah, I think I read somewhere that very early in the pandemic, there was a lab doing research on just how effective different kinds of fabrics were, and how many layers of fabric you needed to stop a lot of the virus from, passing through. And that was pretty interesting.
Yeah.
Silk was not as effective as 2 layers of quilting cotton, as we all know now. So.
How did you start your collaboration with Kate O'Brien? I'm really fascinated by that project that you have, because you've, well, yeah.
Sure, yeah. So I met Kate at Haystack back in 2015, I guess, and we were both TAs for different classes there, and stayed in touch afterwards. And she maybe in 2017 started a PhD in math education in Manchester, England. And I'd been in touch with her just off and on at that time, but I have a deep interest in math, and essentially just pursued her, chased her down so that I could, to try to work with her. And it is, I mean, it's a collaboration where we do a lot of talking, we do a lot of writing. We have met up a handful of times for some intensive kind of workshopping of ideas. And, in some ways I still don't know what it is that we will be making, but we are having so much fun. So
Well, it definitely looks like you're having a lot of fun. I just saw your new website not too long ago, and I was really impressed how much you've done. Every time I look at your website, it's something new. It's something drastically has changed, but it's exciting. I mean, I've known you since I've known you. You're kind of my math friend. So it's just very interesting how that's developing. Let's see, do we have any other questions waiting?
Yeah, we do. Barbara's asking, does anyone have thoughts on how to remove the nanoplastic from the oceans? I'm going to punt that one to Lindsay.
Good question. I'd have no idea. That's a tough one.
That could be a good topic for a next session for our affinity group. And we can find the person that knows that answer.
Yeah, I mean, I think there are certain things we can do to not put more in the ocean. So there are some kind of devices or filters that you can put in your washing machine, for example, things like that. So we can be more proactive on that end. Industry might have to step up as well.
Oh, Leva Apson, she's wonderful. She just shared a great link. Jen Bervin's work on silk poems. I'm definitely a fan of Jen Bervin's work. Let's see, are there any other questions that we could tackle here? Or any questions for each other, guys?
I think the one that Isaac, you spoke to a little bit ago, but just the question on how do we develop research questions, or do they emerge intuitively? I think that's an interesting question for all of us to answer. And yeah, I mean, I think for myself, I definitely don't proceed according to a logic outside of my own self. I Yeah, I think the research questions often emerge actually more when I'm very much in the middle or towards the end of working with and around an idea. And often they're very tangential to where I started. So yeah, how about other people?
I already answered that one. So what do you think, Lindsay? How about you?
I would say that probably for many years to come, I'm going to be working on water issues. I'm currently finishing up work for understanding how the Army Corps of Engineers manages the Mississippi River. And I'm beyond that. The project's almost finished, and I'm in the very early stages of connecting issues around land and sea and the anoxic zone in the Gulf of Mexico, and how farming needs to change in order to keep more of the nitrogen and phosphorus and potassium on the soil itself, and how farming practices affect fishing stocks, or like I said, those dead zones in the Gulf of Mexico. So I really proceed from interest in water issues. I think going to sea really gave me a different perspective, an even larger perspective on water than I got at the wastewater treatment plant. So, some serendipity is involved. It's not, like Heather said, it's not a linear kind of approach to choosing your question, and your question gets refined as you speak to people. So it's a hard question to answer, actually.
I echo what Lindsay said. It starts as a lack of knowledge, and you just want to learn more and understand more, and that just sort of snowballs into other areas that you also don't know. So for me, it's an inquiry and really trying to understand something that I don't know. And whenever you look at something, even if you think you know, there's always new insights when you talk to collaborators and see new information. So just questions and following through.
It's also challenging, developing these questions when you're working with someone that maybe doesn't understand, or is new to your fields. I mean, I'm thinking of the way your approaches to things, Lindsay, with your partnerships. Elizabeth and I have been working together for a long time, and I mean, I've always just enjoyed working with Elizabeth, so that makes it always is really natural, because we're just sharing and understanding our work. But when it comes to putting wastewater treatment with textiles, like how do you even come to that common question and to create a project?
Yeah, it's curiosity. Actually, I think what drives all of us is we're curious about the natural world, or we're curious about a corner of a particular area of textiles. So yeah, curiosity is a really powerful motivator.
So before we have to be wrapped out of this, I want to thank you all for taking the time this afternoon to talk. And I want to thank my fellow co-hosts for working with all of us to make this is an exciting venture. I mean, and this combination is amazing. So thank you to all of you and all of those who came.